Okay, so now I've got an example where we're determining whether a collection of polynomials is a linearly independent set within the vector space P2, which P2 refers to the collection of all polynomials degree 2 or lower. So that's what the 2 refers to there. When we say vectors, then, we're referring to the elements of P2. So we're referring to polynomials degree 2 or lower. And I started to write the definition of linear independence here. So we want to work from that definition again, which is the equation C1 times vector 1, which again, vector in this case refers to the polynomials, plus C2 times our second polynomial, I'll call it V2, C3 times the third polynomial equals the 0 vector. If this has only the trivial solution, then the polynomials here are linearly independent. If there is a non-trivial solution, so say C1 is -1, C2 is +3, then we have a non-trivial solution. That means that these polynomials are linearly dependent. One other thing, so 0 vector refers to, takes different forms, let's say, depending on the vector space. With any collection of functions, so something like P2, when we talk about the 0 vector, we're referring to just the constant function, let's say p of x equals 0. We're referring to just the constant 0 function when we refer to the 0 vector for any collection of functions. So if I want to set up this equation, but with these particular polynomials, then we would set this up as C1 times the first polynomial, x squared minus x plus 3, plus C2 times the second polynomial, 2x squared plus 3x minus 1, plus C3 times the third polynomial, -5x plus 7, equals the 0 vector, which in this case is just the constant 0 function. So it just equals 0. So now say you distribute your scalars, C1, C2, C3. So C1 x squared minus C1 x, not x1, just x, plus 3 times C1, 2C2, and I did it again here, sorry guys, x squared, 2x squared, this should be 2x squared here. So 2C2 times x squared, 3C2 times x, minus C1, or sorry, minus 1 times C2, so minus C2. C3 times this, so minus 5C3x plus 7 times C3 equals 0. So with a problem like this, what I like to do is now combine powers of x. So combine the x squared to collect the x squared terms. So here and here, right? So the coefficient of x squared is C1 plus 2C2. Okay. Now if we combine our x to the first term, so that's here and here and here. So plus x times coefficient of x will be -C1 plus 3C2 minus 5C3. Okay, and then constant terms, we have the 3C1, the -C2 plus 7C3. Here's your constant term, equals 0. So if this is equal to the 0 function, then that means that every one of these coefficients would have to be 0. The constant term here has to be 0. This whole expression here, which is your coefficient of x, has to be 0, and the coefficient of x squared has to be 0. So we have this expression here equals 0, this expression here, equals 0, and this expression here equals 0. Okay, and that looks fairly complex. So 3 equations, 3 unknowns. So I think what I'm going to do is erase this top part here and write down that system of equations. So where I need some music playing in the background. Just we don't need that either. Okay. So we have this C1 plus 2C2 equals 0. And then this one, so negative C1 plus 3C2 minus 5C3 equals 0. And then this one, 3C1 minus C2 plus 7C3 equals 0. Let me say that sometimes this system of equations, it's easiest to solve just with some substitutions. But in this case, yeah, I'm just going to go for a matrix. So we've got a system of 3 linear equations with 3 unknowns. We can express this as an augmented matrix. So -1, 3, and then 3, -1, 7, 0. And then row reduce this thing to find the solutions. So I would do just row 1 plus row 2 to get a 0 in this position. So let's see. So that'll give us 0, 5, -5, 0. And then -3 row 1 plus row 3 to get a 0 in this position. So that'd be -3 plus 3, -6 plus this, 0 plus 7, 0. Okay, so now if we do 1/5 times row 2, we get that. And then if we do 7 row 2, right, plus row 3, to get a 0 in this position here, that will give us, let's see, 0 plus 0, 7 plus -7, -7 plus 7, and 0 plus 0. So at this point, we see that, well, so here are your pivots, here and here. Column 3 is not going to be a pivot column. So C3 is a free variable. Remember that whenever you have a free variable, then we're guaranteed to have non-trivial solutions, because that means that C3 can take on any value. We can write a solution using any value for C3. So certainly C3 does not have to be 0. So then automatically we have at least one, well, we have infinitely many solutions that are non-trivial then for all the non-zero values of C3. So that guarantees us non-trivial solutions. And let me be clear. So non-trivial solutions to this equation. So C1 times the first polynomial plus C2. I'm just going to draw squiggles for the polynomials. Back when we wrote that equation, plus C3, oops, times the third polynomial equals 0. We're guaranteed non-trivial solutions to that equation, which means that those polynomials, I'm not going to write them out again, but those given polynomials are linearly dependent. And I should put these polynomials. So I don't want to just say in general, polynomials are always linearly dependent. That would be wrong. So just these particular polynomials that I gave you in the example problem are linearly dependent.